In Part 3 of the Unit 10 notes, we are going to be covering Gay-Lussac's law and the combined gas law. In 1802, Joseph Gay-Lussac developed Gay-Lussac's law, in which he described the direct relationship between the pressure and temperature of a gas when the volume remains constant. He designed experiments similar to the one shown below. In order to perform calculations using this law, all temperatures must be in Kelvin. To convert from Celsius to Kelvin, add 273. So this is the same process that we used in Charles' law in the previous video, and the same one that we will use for each of our gas laws. In our experiment, which we see here, we have an initial pressure of 2 atmospheres. We are in a sealed container where this lid is immovable, so it is at the same distance in the beginning and the end. By adding this flame on the bottom, the molecules are now moving faster, which means that they are colliding with the walls with a greater frequency and a greater amount of force. Since the container is not able to expand, the pressure increases, and here we can see that it goes from 2 to 4, so it doubles. There are two variations of this law. We could say that our pressure divided by temperature is equal to some kind of constant, or we can say that our initial pressure divided by temperature is equal to our final pressure divided by temperature. In our first calculation, we have gas in a used aerosol can, which is at a pressure of 103 kPa at 25 degrees Celsius. If the can is thrown onto a fire, what will the pressure be when the temperature reaches 928 degrees Celsius? Now, just like with our previous gas laws, there is a specific way that you need to write everything out to receive credit when you take the test. We're going to start by writing out each of our variables. So we have pressure 1, temperature 1, pressure 2, temperature 2. My initial pressure was the 103 kPa. My initial temperature is 25 degrees Celsius, but I can't use Celsius here. So I'm going to add 273 to get 298 Kelvin. My second pressure is unknown, that's what I'm trying to solve for. And my second temperature, I have 928, and I have to add 273 to that. So it's going to be 1201 Kelvin. I identify my law. This is a Gay-Lussac's law question, so I have P1 over T1 equals P2 over T2. And then I need to solve for my missing variable, in this case, P2. I can multiply both sides by T2, and that gives me a new version of the equation with the variable that I want isolated. I'm going to rewrite this so I have P2 is equal to T2 P1 over T1. And then I'm going to plug in each of my numbers from what I wrote out over here. So my temperature 2 is 1201 Kelvin. My pressure 1 is 103 kPa. And my temperature 1 is 298 Kelvin. The Kelvin is going to cancel. I'm left with a unit of kPa, which is acceptable for pressure. And I end up with 415 kPa, which is 3 significant figures, which matches with what I have here. All right, for our next question, I'm going to write down each of my variables. So I have a P1, T1, a P2, and a T2. The pressure of gas inside a canister is 5.00 atmospheres at 25 degrees Celsius. So just like before, since this is Celsius, I'm going to add 273, and that comes out to 298 Kelvin. If the temperature falls to negative 10 degrees, so that would be 263 Kelvin, what is the new pressure inside the canister? So I need to solve for P2. So I start with P1 over T1 is equal to P2 over T2. Multiply both sides by T2. And rewrite my equation. My temperature 2 is 263 Kelvin. My pressure 1 is 5.00 atmospheres. and my temperature one is 298 Kelvin. My Kelvin is going to cancel out, and I'm left with atmospheres. When I multiply and divide across, round for significant figures, I have 4.41 atmospheres. Next up, we have the combined gas law. There are many instances where the pressure, volume, and temperature might all change. Boyle's, Charles, and Gay-Lussac's laws can be joined together to create the combined gas law. In order to perform calculations using this law, all temperatures must be in Kelvin. To convert from Celsius to Kelvin, we add 273. So like I said, that is true for all of our gas laws. If we were to combine our Boyle's, Charles' law, and Gay-Lussac's law into one equation, we would have pressure times volume divided by temperature, which is equal to some kind of constant. The more common version of this equation that we are going to use is P1V1 over T1 equals P2V2 over T2. A gas at 110 kPa and 30 degrees Celsius fills a flexible container with an initial volume of 2.00 liters. What is the new temperature if the volume decreases to 0.58 liters and the pressure increases to 440 kPa? All right, so I'm going to start by writing out my P1, V1, and T1. And then P2, V2, and T2. The gas is initially at 110 kPa. And for my temperature, I need to add 273, so that's going to be 303 Kelvin. And the volume was 2.00 liters. The pressure is 440 kPa at the end. The volume is 0.58 liters. The temperature is unknown. I start by identifying my law, which I know here is combined gas law. And I need to identify my missing variable. It's going to be T2, and I need to get this by itself. Now this is similar to the same type of question in Charles' law where I described how to solve for T2, or a variable on the bottom. You could start by dividing both sides by P2 and V2, but what you're actually going to solve for is 1 over T2, which means you would need to flip the numerator and the denominator on both sides. And since for some students this can be a little confusing, instead I'm going to start with the cross multiplication method. I can multiply T2 up to the opposing side and T1 up to the opposing side. That gives me an equation of P1 V1 T2 equals P2 V2 T1. And when all of my variables are in a straight line like this, it's a little bit easier to solve. If I want to get T2 by itself, I just need to divide by my other two variables, P1 and V1. And now I have a new version of the equation. So I'm going to rewrite that down here. So I have T2 is equal to P2 V2 T1 over P1 V1. And now I just need to plug everything in. I have 440 kPa, 0.58 liters, and then my initial temperature of 303 Kelvin. It's all going to be divided by my first pressure, which was 110 kPa, and my first volume, which was 2.00 liters. The liters are going to cancel, the kPa are going to cancel, and I'm left with Kelvin, which is an acceptable unit for temperature. I'm going to multiply everything across, and it is going to be 350 Kelvin. Now in this particular question, it says what is the new temperature. It doesn't specify what unit it's supposed to be in, so I can leave my temperature in Kelvin. If it was specific and asked what type of temperature it was in Celsius, I could always subtract 273 in order to get back to the original temperature. All right, for our next combined gas law problem. The volume of a gas-filled balloon is 30.0 liters at 313 Kelvin and 153 kPa. What would the new volume be at STP? Now, if you're not familiar with STP, that stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius, which is 273 Kelvin. Standard pressure is 1 atmosphere, which in this case, since we are talking about kPa, would be 101.325 kPa. And this you can get from that equivalency, which I gave you in the first notes video. So some students get confused with this type of problem because there aren't enough numbers. They have a pressure, a volume, and a temperature, but they don't have the other ones. So this is the trick to that. Two of the numbers are actually just based on the fact that this is STP. So now that I have that, I'm going to write out my P1, V1, T1, my P2, V2, and T2. My initial pressure is 153 kPa. My initial volume is 30.0 liters. And my initial temperature is 313 Kelvin. My final pressure, I'm going to use the 101.325 because I want the kPa units to be able to cancel in the end. I'm looking for the final volume, and my temperature, since it's 0 Celsius, is going to be 273 Kelvin. From here, I have my combined gas law, P1 V1 over T1 equals P2 V2 over T2, and I am trying to solve for V2. Now, I could use the same cross multiplication method that I used before, cross up T2 to the opposing side and T1 to the opposing side, but since V2 is already on the top here, I can also just divide both sides by P2, because that would cancel, and multiply both sides by T2. Doesn't really matter which one you choose because you'll get the same answer either way. From here, I'm going to rewrite my equation, so I have V2 is equal to T2 P1 V1 over T1 P2. And now I'm going to plug everything in from here. So my T2 is going to be 273 Kelvin. My pressure 1 is 153 kPa. My volume 1 is 30.0 liters. T1 is 313 K. P2 is 101.325 kPa. Temperatures and pressures cancel. I'm left with the unit of volume. Multiply and divide across, we end up with 39.5 liters. That concludes part 3 of our Unit 10 notes. When we come back for part 4, we'll be covering the ideal gas law, Dalton's law of partial pressure, and Graham's law.